We're still talking about chapter 15, which is the bulk metal deformation or bulk deformation process, chapter 15. Still remaining chapter 16. This is the next chapter and last chapter. In chapter 15, we're discussing about rolling, forging, extrusion, wire and bar drawing. This is the four process that, as you know, we're discussing in chapter 15. Rolling already finished. We already finished rolling, and now we talk about foraging. Rolling already, this one already finished. Now we talk about foraging, still remaining extrusion, wire and bar drawing in this chapter. Now we talk about foraging. Last time already we started and we do analysis, a numerical analysis in foraging operation. Today we will continue discussion about the foraging operation. We talk about several die foraging operation. Several die forging operation like whatever we call fillering, edging, and coining. Fillering, edging, and coining. This is the three processes that we're going to describe: fillering, edging, fillering, edging, and coining. This is the fillering. Fillering act as a word fillering when set fillering, something like this. Here is somehow is a forging operation performed to reduce the cross section. So this is a bar here. The process forging operation, we hammering the workpiece to reduce the cross section and redistribute the material in a work bar, as you can see, in preparation of subsequent shaping process, something like this. You hammering the workpiece, you reduce the cross section and redistribute the material in other part, as you can see here. We call it is the fillering. Fillering here, the shape, the die shape here is the convex surface. This is a convex surface, so this is a die shape. They call it is a fillering. Edging is exactly same, but the die shape is somehow different, which is a concave surface. So here the die shape is a concave surface. It's also doing same. So here the die reducing the cross section in somehow and increasing the material in other place, redistributing the material in a bar. This is whatever we call edging. Next is coining. Coining is hammering the workpiece to reduce the cross section and increase the length. So it is actually done along all the lengths. So it's something like here. Then you're hammering the workpiece, you reduce the cross section and then length will increase. Because you're hammering all the cross section, not in certain area, but all cross section from beginning to the end, then length will be increased, as you can see. This one also they call it is incremental forging. Some they call it also like this. Let me show you a video to make easy for you to understand or differentiate between these two or three applications. It's coming. Yep. This actually is fillering, edging, and also cooking. This is about the part in first you heat, must become soft, and then this is a fillering. The fillering here, you see this. This is a convex shape. Convex shape, you hammering the work. You reduce the cross section. You reduce the cross section here, as you can see, and redistribute the material in a part. This is a fillering. This is a convex shape. If it is concave, then this is edging. So this is a fillering, right? This is mechanical hammer, automatic, not hammer by hand, but mechanical hammer. This is cogging. Cogging here, when you said cogging, cogging is reducing the cross section, all cross section, and definitely when you increase the cross section, when you reduce the cross section length, you can see, can you realize? The length will increase. The increasing the length, so reducing the cross section. This is the cogging. So as you can see, reducing the cross section, and definitely when you're reducing the cross section, length will increase. Right. I hope it's clear now. Right. So go back again to the slides. Then again, this is furring. Furring is this is a convex shape. This is a convex shape. Convex shape here, you reduce the cross section and redistribute. This is a furring. Edging is exactly same, but the shape of the die is different. This is a concave shape, right? And finally, is cogging. Cogging is you hammering the workpiece material, you reduce the cross section and then increase the length of the work part. We will move to the next section, which is not open die anymore. We have open die, closed die, and impression die. This is the impression die forging. Now we just finished open die forging. This is the impression, second section in the forging operation, which is the impression die forging. The word impression die forging is, they call it in some time flash die forging. Flash die forging. So what is the flash die forging? Actually, this is a part you put in a heat, you heat it, and when it become hot, then you start deforming it. This is the upper die and lower die. This is the workpiece. You apply pressure. When you apply pressure, material will start to deform. Material will fill the cavity, and then part of material will exit from here and here. So this is extra material. This is the part we need to have. This is extra material here. So extra material will move from here and here. We call it flash. This flash we need to cut at the end of the process. We need to cut as this is whatever we call impression die. So impression die flash will be created. Flash will be cut. Extra material, flash, extra material will cut together part. Okay, something like this. Finally, we need to get this part. Initially, we start with this kind of. Can you see that this is the initial workpiece? Initial workpiece is cylinder. You hammer, you hammer, you hammer. When you hammer, you shape. This is a die. This is a die, right? Then you use this one initial raw material. You hammer and you hammer. You shape. You become like this. This is the extra flash. This is a part. Then you need to get the part. This is a part. This is a flash. Flash is a extra material. It is associated with a part. We must have it. Then you need to cut. This is a flash. You scrap it. This is a part. Someone don't believe me. This one start with this one and finally end with this one. He don't believe. It seems like this. Okay. Then let me show you. Let me show you a video to describe this one. Then you will believe. Coming. Yep. Come. This is you see we hammering here. This is a hammer, mechanical hammer. This is a part is hot. This is a part here. It is cylindrical. See, it is shaping here. Initially, it was cylindrical shape. You see, it is cylindrical shape. Again, you see, it is cylindrical shape. Initially, it is cylindrical shape, and then now hammering, it deform. That's exactly same. So it deform in the part here. You see? So the deformation. So you see what happened at the end. Initially cylindrical shape, but finally you get the part as you can see here. Whatever shape can be done. Okay, get back to slide again. Then this is deformation actually. You put the part, you apply pressure, This is a flash. Flash is the extra material. Flash here is the extra material you need to cut. Actually here also. So it happening. So this is the die, for example, if you have the die, then this is the upper and lower, which is connected with the hammer. Upper and lower, then connected to the hammer, and then here you put here and here and here. One time here, one time here, one time here. So it depends. Finally, you obtain the shape, but finally you need to cut. It takes the part and you get the flash. So flash is scrap and the part. This one we call impression die forging or flash die forging. Sometimes we call like this and sometimes we call like this, right? So this is a process. So let me tell you, this is the upper, this is the lower. When they hammer, this one will be created. This one we call flash. This is a part actually. Let me tell you, this is a part. This is a web. This is a rep. It depends on the shape of the part actually. Different shape. You can get different shape. Anyway, this is a web. This is a rep, and so on. This is a flash. This is a flash here. Can you see that? This is a flash. Exterior will move here, and extra material move here. And there here is the land. We call it the land. This is the land. And here this is a flash. This is the land. Land here apply friction. There are a friction between this material. Not easily material to flow actually. Not easily because there are a very high friction here and here. This friction actually, let me tell you, the friction here and here apply back pressure. Apply back pressure. Apply back pressure mean friction not easily flows the material. Then friction apply back pressure. Friction in the land. Friction in the land apply back pressure. Why apply back pressure? Apply back pressure to push the material to fill all the cavity perfectly. This is the benefits of having flash here and here, or the benefit of flash. Actually, flash is really nice. So flash is extra material and finally going to cut, yes, but the friction here and here in the land apply back pressure. This back pressure important to push the material, not easy to flow here, difficult, very difficult to flow here, then flow here and here to fill all the cavity, as you can see here, perfectly, without any defect. So this is mainly is the issue. So this one later will be cut. As you know, this is the extra material or extra flash material. And I can see this is upsetting start here. Can you see that? This is the half cross section. Upsetting start here, more upsetting. Flash is started, as you can see, flash is starting, and you apply more flash here is getting bigger and difficult, very difficult, become material, very difficult to flow. This one applying back pressure to increase. So you can see here, this is load and this is a distance. Then when you come from up, move, then you see the load is low, and then when you hit the flash, this is the forging energy, and then when flash started here, see the load is increasing significantly. You can see, so increasing significantly, as you can see here, because of flash started, then load is applied. You need to apply higher load. The material, instead of material flow outside, flow inside to fill all the cavity. Then you can see that this is a die actually. This is a shape. Initially, you start with certain raw material, and then when you're hammering the workpiece, finally you obtain the shape as you can see here. And you can see here, this is the load actually. Load when flash start, probably flash start here at the then load will significantly increase because flash not easy to flow material, then increase to material fill the cavity perfectly. Force here also can be obtained as we described on the analysis last class, that force equal to Kf Y flow multiplied by area. Y flow K epsilon N, and area is a final area or projection area, and Kf is a factor, or we call foraging shear factor, can be obtained as we described earlier in the last class. There are overlap sometimes. Sometimes there are overlap. Overlap mean between machining and forging. Or for example, same part we can obtain by foraging, this by foraging operations, this is by machining. Then you can see there are overlaps. So foraging can, machining can. Foraging means this way. This is a foraging operation, you can do this one, or you can do by machining. Machining, I mean use cutting. So this part, same part can either do by machining or do by foraging. So what is the decision? Shall we do by machining or we do by foraging operation? You need to understand what is a feature, what is the big differences between both cases. Then you can see advantages of foraging operation compared with the machining is a high production rate. Foraging actually produces one in very short time compared with the machining, so faster production rate. This is the one. Less waste of material in foraging operation. Machining, you remove big amount of material, you get big waste. Here, lower waste of material, great strength. Why great strength? Because here you see the grain here is cut. You cut the grain. You cut the grain of the material, but here no cut. Volume is same, and you big deformation, you flow material around. Then this one strain hardening will associated with this one, great strength you obtain in case of forging compared with machining. Favorable grain structure and orientation. Here you cut the grain, probably this leading to, as you know, some micro cracks and some defect compared with the forging operation. However, machining have big advantages, which is you know even without I'm telling, is the dimensional accuracy and geometry. The most precise and accurate geometry can be obtained by machining. Actually, in many cases, foraging also followed by machining. However, you can do shaping by foraging operation, and little machining could be done. Then you save the time, you save also the cost. So machining is considered here. Probably we can manufacturing by foraging operation. Little machining could be done as a subsequent process to obtain the accuracy and the precision. Right. So this is issues. Then we have this leading us to whatever we call is a precision foraging feature. Precision foraging feature. This is a precision. This is a foraging operation. This is a foraging operation. And a foraging operation actually because of, please listen to me carefully, because of in a foraging operation we have lack of geometrical accuracy and close tolerance. We keep a bigger distance. We keep bigger dimension in a foraging. When we do foraging operation, usually we keep a bigger dimension, and then this kind of foraging part will be taken for machining to remove this kind of additional area. We keep to get the precision like this, right? So this is the precision part. This is the part shaped by foraging. Someone will ask me why we do this. Why we have to keep some distance? Why we just simply just make the part exactly as we would like to have without any additional material? Actually, for many reasons. In case of you heating the material and you working as a hot working, not cold working material, expand and contract. Then when you heating this material expand, and when you deforming material, you deform material what is hot. And later when you cool it down, material contracts. So you don't know what will happen, how to expand and how contract. Then you must keep dimension bigger. You cannot actually know exactly. So finally, after you finish, you bring this one to machining and you remove the extra part. Then you get the desired dimension as you wish. Then you ask me, then probably cold working is fine. Sometimes cold working is not okay, but cold working, if you can work with a cold working, it will be better. Still, even in cold working, we have to keep dimension is bigger. But how to control this one? How to minimize the machining? This is the issue. Actually, we always looking for minimizing the machining as we can. So if you can do the center, if you can do the center in forming, directly in forming, if you can eliminate machining, will be excellent. If you can eliminate machining, excellent. Why? Why? Someone said, why we eliminate machining? Just simply do machining after form, because you pay money. More process meaning more money. If you can just in very simple way, if you can just achieve it, the process totally achieved by foraging or by forming without need to machining will cost less. Always be looking for money. People looking for money. How to reduce the cost, how to increase the profit. This is the issue. A meaning thinner section or a complicated geometry, simplifications of process, you reduce the draft requirement and closer tolerance. If you can achieve this one directly, we call it precision foraging. So precision foraging operation is to reach to this one directly by foraging and to eliminate or at least minimize the required machining after the foraging operation. Right. Next section was the last section in a foraging operation, which is the closed die foraging. Closed means flashless. We call it flashless. Here is a flash. To let you know the difference, this is a flash. When you apply pressure, flash will be created. I understand? So this is a flash or impression die foraging. Here is a flashless. When you apply pressure, no flash, not a long flash. So this is a closed die foraging. This one we call it closed die foraging, flashless. Actually, this is a kind of improvement to achieve or to move towards the precision foraging, as we described in the last slide, to reduce the need of machining. Because here, if you have a flash, you need to cut here and so on. So this is a flashless. So it's considered as precise machining, precise foraging. When you apply pressure, this is a part. Then you have to accurately calculate the volume. This is a flashless. Then you have to accurately calculate the volume. You know the volume is constant. Then you must calculate the volume accurately, so you finally obtain exactly the desired dimension. So this is the closed die foraging, flashless foraging, and this one considered as precision foraging act. They consider as precision foraging, right? As an example of closed die foraging is a coining. Coining here, material will flow act. This is the initial part, that is a workpiece. You put here and you apply pressure, material will flow, and finally you deform material in somehow with final, no machining, no additional part here, no additional work actually. This is done. This is done and final. This is the final part directly you take use. So this is considered as a precision foraging. So this is a flashless, closed die flashless, no flash, no cut. There are no any subsequent process. So it's done, finished. Simply you take and use directly from here. So this is a net shape, whatever we call net shape, and we call it also precision foraging. The hammering process, hammer is a machine that we use to do the foraging operation. This is a hammer, right? So this is a hammer, and hammer being used to do the foraging operation. We have two types of the hammer: gravity drop hammer, power drop hammer. Gravity drop hammer and power drop hammer. The word gravity drop, let me tell you, gravity drop is the ram. This is the ram. This is as you can see here, this is the actual photo. This is a figure to show. This is a ram. This is a piston rod. This is a frame. Then here, this is a ram. This is the structure of the hammer. So in a gravity drop, this one fail under gravity. The ram fail under gravity. We take it up and then we leave it. It is very big and very heavy. So we take it up and leave, and it drop under the gravity. This is, you call it the gravity drop hammer. The second one, power drop hammer, accelerated. The power drop hammer accelerated by using the pressure, air, or steam to hammer the workpiece. This advantages impact energy. This is very impact. Boom, boom, impact energy transmitted to the floor to the other machine and surrounding, commonly used in impression die forging operation. This is the power. The gravity one is nothing. Is you to just take it up and then leave it to drop under the gravity. The power one, the power drop hammer, power drop, either you can accelerate the ram. This is the ram. You accelerate the ram by mechanical, by this one we call a screw. This one we call fluid or hydraulic. This is mechanical, mean rotating. This is the rotating axe. And we're translating rotational motion to linear motion. We're translating, this is like very similar to internal combustion engine. So we're translating rotational motion, as you can see here. This is a rotational motion to linear motion up and down. So we driving the ram by using this guy, same also here. By using screw here, this is rotating. By friction, this one is rotating. This screw moving up and down. Then when the screw moving up and down, ram moving also up and down for hammering the workpiece or pressure workpiece. Here by using fluid, fluid is you pumping from down to up, then pushing up. You pumping liquid or oil from up to down, then it's come up and push down, then moving up and down. This is the three type of the power drop hammer, right? Other deformation processes related to the forging operation. Other deformation process related to forging operation. What? Whatever we call heading and upsetting. Upsetting and heading. Heading, the word heading means to create the head. It's like this. I would like to create the head. This word heading. Upsetting means you apply compression. Upsetting, which is an open die or closed die. Forging is up. Forging generally upsetting, right? And heading mean you create the head of the bolt here. Then this is a process, we call it heading, upsetting and heading. This is the operation. This is the first step, second step, third step, and finally head will be created. This is the head. This is the head, right? So head is created. So first step actually, this is a wire stock feed into to stop. This is a wire. This is a wire. It is a wire like this one. It's move until it stop. Stop here. This is a stop location. So it is stop here. This is the first step. Second step is grabbing the die. This is a here gripping the die, gripping the wire. Then gripping, apply pressure. This one will not move in this direction anymore. A stop is removed, and then you apply pressure. Third steps, you apply pressure. Whenever you apply pressure, material here will be deformed, and finally material will fill all the cavity, which is head. So we call it heading. So you manufacturing here the bolt head. So heading, upsetting and heading. Not only this shape, but several shapes also as well. Like this one, nail, you can make head of nail. You can make this shape, which is round. You can make hexagonal. You can make a taper. This is a taper. This is a hexagonal. This is square. This is round. This is a nail. So several type of heading can be produced. As I show you here in the figure, can be produced, right? Next, we have whatever we call swagging and radial forging. This is the next other processes related to forging operation. Swagging and radial forging. Right. What is a swagging and radial? Swagging actually, you hammering a workpiece. You're hammering workpiece to reduce the cross section. Initially, it is diameter is big, but you're hammering the workpiece to reduce the cross section and become this one. So this whatever we call swagging. You're hammering the workpiece to reduce the cross section, and please listen to me guys, swagging here, the die hammering and rotating. Like here is two hammer. Look to this one, it's two hammer, one up and one down. It hammering and then rotate to hammer other direction. So it hammering in this direction and then they rotate to hammer this direction and then rotate to hammer in this direction and rotate to hammer in this direction and then rotate to hammer in this direction and so on. So you can see here the die rotate. The die rotate. So hammer and rotate. If hammering up and down, then not all surface or perimeter will be hammered. If these two die only hammer here, then not all perimeter will be hammered. Then it must rotate to hammer the other perimeter of the surface. So you can see here it's clear. Then die here rotating. Maybe two die, maybe three die. It can also. So sometimes two die, sometimes three dies. So they call it swagging. So swagging, you're hammering a workpiece to reduce the cross section. Here in a swagging, you die hammering and the rotating workpiece is not rotating right. So this is a swagging. In radial forging is exactly same like swagging. What is the difference? The difference is that these guys, I mean the die only hammering workpiece is rotating. It's easier. They rotating the workpiece. So workpiece, this one easier. So die not rotating, just only hammering. Die only hammering, rotating workpiece is rotating. This is whatever we call swagging, right? Radial forging, and this is the many application. Reduce the cross section, as you can see here. Here, taping the tube also, tapering the tube here. This is the tube actually. Tube meaning hollow cross section. This is a solid section. This is the hollow. Somebody said that hollow cross section. So what will happen if you try to hammering the hollow cross section? You destroy the internal surface. Yes, I agree with you. So how we can solve the problem in a hollow cross section? How we can hammering the hollow cross section without destroying the internal surface? Actually, simply I tell you that we added internal mandrel. We added whatever we call internal mandrel. What is the internal mandrel? Actually, put sand. They put sand. Do you know the sand? رملة يا شباب. عارفين الرملة؟ هم بيحطوا الرملة جوه. الرملة لما يعني تعمل هامرنج للرملة، الرملة redistribute when you hammer, then the cross section will reduce, and then hammer, then the sand will redistribute again with the size, and in the same time applying a pressure to maintain the dimension of the cross section. So they put internal mandrel to maintain the internal dimension, to not collapse the internal dimension. Here also necking. The word necking, to make neck. This is also swagging and radial forging operation. Also, if it is hollow tube, we put sand. If it is solid, it's fine. If it is hollow, you put sand inside or internal mandrel. Here is the pointing. Pointing means to create point. Then by also swagging or radial forging. Here also necking. You create neck here. It was initially like this, and then you creating necking by using swagging and radial forging, right? Probably if it is hollow, you know what to do, right? Exactly, you need internal mandrel inside. This is the roll forging. Actual roll forging, we describe or we discussed this one previously in a previous chapter in rolling operation. This is roll. It is mixed between roll and forging. They deforming the surface, not only rolling but also they deform the surface of the roll to hammering the workpiece or to shaping the workpiece. So it is kind of mix between rolling and forging operation at the same time, as you can see here. This is another process could be done by forging operation, which is creating ball. creating ball in a ball bearing to be used in a ball bearing. It could be done by using whatever here is upsetting cylindrical plank, upsetting of a cylinder. This is a plank here, cylindrical plank, cylindrical. It is a cylindrical shape. We'll make it sphere. It is initially cylindrical plank. We will create here a sphere. So you do upsetting here, you put the plank, you do upsetting, then it will be spherical shape. And finally, you do grinding. You need to do grinding after the process. After completing the process, you need to do grinding for be sure a complete spherical shape. It could be done by rolling also. This is whatever you call a skew rolling. This is a part cylindrical part you put here, and then skew rolling. Then they can create this kind of semi-finishing, and then you need to do also grinding. It must be followed by grinding operation. Okay, next is whatever we call orbital forging. With the word orbital forging, it is a way, listen to me guys, it is a way to do forging operation, but we do partial forging at the time. We not do full forging, but partial forging at time. Why we do partial forging? To reduce the load actually. The idea is you supposed to, this is a part, this is the workpiece, and then we need to simply apply pressure on this workpiece to fill the cavity. However, to put the pressure, if you apply pressure in all the surface, then you need to have, because pressure multiplied by area, right? You get the force. So you need to reduce the area. Don't apply the pressure in all area at the same time. This one will reduce the force, definitely. So they do whatever they call is orbital forging. Orbital forging, this one is rotating. This is a spindle. This is a spindle. You see, this is a spindle here. Please listen to me carefully and try to imagine this is a spindle, right? The spindle, this guy is a spindle. Spindle is rotating in orbital direction. Then it is rotating around in somehow moving. It is pushing here and then here and then here and then here. It's rotating like this. Sometime pushing here, other time pushing in other direction. So it is sometime pushing here, sometime pushing. So it is rotating around to push every time push partial area, not all area. Finally, it will come apart, but partial contact every time. This you call it as the orbital forging operation. The idea is how to reduce the force. You can do the same process with is lower force and lower power and definitely lower machine. You can do actually many deformation for many things like gear, for example, in create gear. This is the orbital forging to create gear. This is a gear. Can you see that? This is the one produced. But here deformation is done partially. Partial deformation, every time you do partial or you creating here this kind of deformation. This is a guy here, this is the upper die, lower die is exactly the same. Upper die here is rotating partially, so partially to do the deformation, then finally get the operation at lower force. This is the orbital forging operation. Next is a hopping. The word hopping actually being used to create the die, to manufacturing the die that being used in coining, for example, or other process. Actually, this die is hard, hard material. This die that we're going to manufacturing is a hard material. So hopping is a hardened punch, is very hard punch being used with a particular tip shaped to create whatever shape you would like to have is pressured into surface of the block. This is a block, which is a part that you would like to produce. But this one is being used to create a cavity here, cavity or shape or whatever. This one, whatever we call hopping operation. Then the hardened steel form called hub is machined, the geometry of the part being molded, and then this one being used later as I mean dye being used for manufacturing whatever other product. Next is whatever we call isothermal forging. Isothermal forging. I agreed with you previously, if you remember, on that. Whenever I said isothermal, you must understand it is heating to same temperature. This is the hot die forging, definitely. This is hot die forging. And the isothermal, the word isothermal is to heating up to same temperature. This one we described earlier. I remember I described to you. We said that the idea or the problem is coming when you do upsetting the hot die forging, hot die forging. When this one, the workpiece is hot and die is cold. Whenever the cold die touches the hot workpiece, we do this is the edge, upper and lower edges is cooling down compared with in the core. So here in the middle, this one will deform laterally, more deformation and less deformation at the edges. You get non-homogeneous deformation, this one reducing to high internal residual thermal stress or thermal residual stress. This one leading to some defects, especially in material like titanium and اللي هي بيسموها material with low thermal conductivity material, low thermal conductivity material, like low thermal conductivity because it's cooled down easily at the edges, but because it is low thermal conductivity, the middle will be very hot, is still remaining very hot, and then you get temperature gradient, very high temperature gradient between edges, and in the middle you get non-homogeneous deformation and leading to many defects. You understand that, right? Then how to solve the problem? We must eliminate the gradient temperature or different temperature between edges and in the middle. Then what is the solution? Solution is the heating up the die. You're heating up the die up to the same temperature, which we call isothermal forming. So isothermal forming is heating air. So avoiding shell of the workpiece in contact with the cold die surface as in conventional forging. This is the one. Then isothermal forging in term applied hot forging operation in which die heated to the same temperature as a hot blank to avoid cooling down or shell of the workpiece. So cooling workpiece is eliminated. Yep, workpiece problem is solved. However, this weakening the die become weak. Why? Because the heating die up to same temperature, which is hot temperature, probably material is, soft material becomes softer. The die material becomes softer. Definitely this one leading to shortening the life of the tool. Right, die made of nickel alloy, you must use high or low thermal expansion material, which is a nickel alloy complex, but good dimension accuracy can be forged easily by using this one. Expensive, but some cases it is unavoidable. Then you must use it. This process sometimes carried out in a vacuum to avoid rapid oxidation in the die material, because die material is really important. But whenever you heat it, then many issues coming into this one. You solve the workpiece problem, but the die still have problem with that, right? Next is the trimming. Trimming is a word trimming. The word trimming is to removing extra material. Someone will say that you told us in a forming operation there are no cutting. Yes, there are no cutting, no material remover, but some cases in a foraging operation, it is associated with extra material and need to be cut, right? Like what? Like flash foraging operation. Flash foraging, as you can see here, this is you start and finally get the part is here. This is the part, right? And this is the extra flash. It is unavoidable. It must be there associated with this one. Then finally, you cannot use it in this way. You must take the part out and then you cut extra material here, which is the flash. Probably you can scrap or you can simply recycle. Then you need to do trimming. Trimming is to cut whatever extra material, then you get the part and so on. So this is the trimming operation. So this is by this one, I think this is the end of the foraging operation. This is the end of the foraging operation. Next is the extrusion. Next section is the extrusion. Actually, extrusion, when you say that extrusion means you apply pressure. You apply pressure on material will exit with the same shape, with the same opening, the die opening shape. This is whatever we call die opening. You apply pressure, material will exit from this side. Material will exit from this side with the same shape of the die opening. So this is a die opening. Initially, it is cylindrical shape. Material is cylindrical. You put cylindrical, you apply pressure, right? You put cylindrical, apply pressure, it will exit from the other side with exactly same shape of the die opening. This, whatever we call, is extrusion process. Right? Then it is pressure. Ram applying pressure. So it is mainly pressure, as you can see. So this is extrusion process. You put the metal inside, you apply pressure. This is a ram. You apply pressure, material will flow. Material will flow, will exit from the die opening with the same shape. So initially cylindrical, for example, you can see that. Can you see that? Initially, in all cases, initially a different die opening, it is cylindrical. So it is here cylindrical. Before deformation, it is cylindrical shape. Then they apply pressure here. They apply pressure here. It is exit. This is a die opening. So it is exit from other side exactly with a die opening shape. Whatever die opening shape will be exit like this, like this, like this. Whatever die opening shape, it will definitely exit from the other side. So this whatever we call is extrusion. Then in extrusion we have whatever we call is direct extrusion and indirect extrusion. Direct extrusion and indirect extrusion. Actually, time is almost finished. Time is almost finished. Then it's better to stop here and next time describe the extrusion in details. Let me stop recording.